Hello everyone, my name is Sarisa Basadie and I am presenting the paper Feature Imitating Networks for the 2020 IEEE International Conference on Acoustics, Speech and Signal Processing. This presentation consists of two parts. The first is a discussion of the theoretical motivation and intuition behind our work, and the second part will be a tutorial that will go through some of the code that we have released on GitHub. Before we dive in, I would like to mention my two collaborators and mentors, Dr. Hassimi from Michigan State University and Dr. Tukail Hani from the New York University at Abu Dhabi. Their ideas and guidance were instrumental for every part of this work. I'm currently a student in both a computer science and a cognitive psychology laboratory. As such, I sometimes get the interesting experience of reading papers from different fields tackling a similar problem. This paper is an example from 2017. Both papers collected the G data during driving simulation using a very similar paradigm. The Jianlian PLOS paper focused on simple models and statistical features of EEG that are known in the psychology community to correlate with alertness. The authors of the Frontiers in Neural Tech paper, on the other hand, who are mostly computer scientists, used a sparse deep belief network instead of handcrafted features. Every layer in these networks consists of random Boltzmann machines that need separate non-back propagation training. This is somewhat emblematic of an age-old tension in machine learning research. Researchers either use handcrafted features, in this case 5 different variations of the entropy measure, or increasingly complex neural networks. Both approaches have their cons, of course. Neural networks are notoriously data hungry, which is an issue that plagues bioinformatics tasks especially, and they are still pretty much black box. Handcrafted features, on the other hand, require expert knowledge and are not flexible at all. In this instance, even if there is a small variation of a 6th entropy measure that would improve the performance, there is no way to learn this adjustment without manual trial and error. In this paper, we introduced the Feature Imitating Networks FINS framework. This is a framework for training neural networks that we believe combines the best of both worlds while overcoming many of these traditional challenges. FINS are basically small neural networks that are trained to approximate statistical features and then, via transfer learning, are used to solve real tasks. Now, since we simply want to approximate a known statistical features, we can generate as much training data as necessary by simply producing random vectors and calculating the output using a closed form statistical features. We have also noted that during training you can even train small layers to replicate a small part of the statistical feature equation, for instance a sum of squares, and then it's possible to combine these smaller layers into a fin by training end-to-end. After we are done training the fins to approximate the statistical features, we can simply deprecate the last layer and add a softmax layer for classification. We then retrain the neural network using the actual data for the actual task that we want to accomplish or solve. Now, this is of course an oversimplification. This is what the fins actually look like usually. We combine multiple fins together and we also add layers after the fins to enable a more complex integration of the different statistical features. But the main idea and intuition is still this very simple process. The following is data for results on our fin using the same driver fatigue EEG dataset that was used and collected in the Gillian PLOS 2017 paper. We used entropy fins as these features were proven to be useful in that paper. Now, as can be observed, fins are especially useful under data scarcity conditions, and they outperform the baselines as well as transfer learning methods such as the VGG19 that are bigger and require more data set to fine-tune. The improvement is both in terms of accuracy and speed. Also, we conducted a Levene's test for equal variance, and we find that the variance in accuracy for the fins is much lower than for the other baselines. This indicates that we successfully decreased the randomness of the neural network initialization, resulting in more robust performance. This is one of 3 experiments that we conducted, but to summarize, fins offer a synthesis of feature engineering and deep learning machine learning techniques. This framework allows for quick testing using modular pre-tuned networks that can improve accuracy and robustness, especially when only small amounts of data are available. If this piqued your interest, please find more comprehensive examination and discussion in our paper. Okay. This is the tutorial part of our presentation. So first we'd like to show you a very general way of training fins. The first thing that you would need is, of course, your closed form equations for the statistical features that you are approximating. Here we have entropy, kurtosis, Kuhn-S regularity, and we even reuse previous packages that calculate these features. Now you simply generate random data, and you need to regularize it. We specifically z-score it and scale it. And we also do a continuous wavelength transform for the data, simply because we discovered that it helps the fins better approximate the features. Now to generate your X, again you simply used a random number generating. To generate your Y values, you use the closed form equations, and to generate your fin, we actually have a number of fins randomly generated in a file or specified in a file, and this function takes these specifications and generate fins, which is simply a dense neural network up to those specifications. The specification also includes some optimizer parameters. You can simply generate the dense neural network from this and compile it with the parameters specified, and you would have a fin that approximates the specific feature that you wanted. This is an example of one of the fins that we trained, and using random data that is not the same one that it was trained on, we can simply look at how well the approximation is. As you can see, the fins do approximate the statistical feature pretty well. And now we can try to use these fins. So you simply load the data of the actual task that you have, and you need to z-score it and transform it into the structure that the fin expects. And then all you need to do is load the pre-specified fin and deprecate the last layer and add the softmax layer, which is what this code here does, and then you can simply run it. We also have code for the baselines and the VGG. We will not show you how to run it due to time constraints, but it's very self-explanatory. Now you can simply load the entropy model, for instance, from the trained models folder that we include. This is the different fins trained to approximate the different statistical features that we use in the paper. And then you simply run the fin after the modification that we specified here, using the actual data of the task that you are trying to solve. And as can be observed, our fins are usually pretty good, especially when we only give it a small part of the data. And we also have code that re-randomizes the fin and tests it, just to show you that it's not really about the model. It's more about the weights that were initialized to approximate a specific feature that we know is useful for that specific task. I hope that this was informative, and please contact us for any questions that you would have. Thank you.